Hello everybody. So today we are going to discuss about median. We already discussed about mean and found that mean of a distribution may exist, may not exist. Mean was defined to be equal to expectation of x. The mean was defined to be is equal to expectation of x, and of course this expectation sometimes exists, sometimes does not exist. For example, in case of Cauchy distribution, expectation of x does not exist, and therefore we do not get any measure of location. M was defined to be a measure of location, but as because M does not exist for Cauchy distribution, therefore we can say that so far we did not get any measure of location for Cauchy distribution. And similar measure of location for any distribution uh, similar to similar to this mean is now can be defined by this kind of quantity median. Okay, so now let's continue with this definition of median. What is this? Median is actually, the basic idea is that median should be the middlemost value. Generally median is denoted by mean. So middlemost value means, suppose if you consider the density curve of a distribution, suppose let us try to draw a density curve of a distribution. Say this is a distribution, and suppose this is the density curve of the distribution. Maybe this is the density curve of the distribution. Okay, and in this kind of distribution, the middlemost point, fully the middlemost point is expected to be the mean value. Hmm. But sometimes the mean value does not exist. That's why we are trying to define some middlemost value, and we are calling it as this mu. And what is the property of this mu? The property of this middlemost value is that on the left of this number there should be 50% probability mass, and on the right side there should be 50% probability mass. Remember, this is the density curve. That means the curve of the density function fx. I am trying to explain this in terms of continuous distribution. A similar explanation can be considered for discrete distribution as well. Hmm. So the basic idea is to define certain middlemost value mu, such that on the left of the function of the on the left of this value mu, the probability or the area under this curve, this much area would be is equal to half, and this much area would also be is equal to half. So that is the basic idea of introducing this median. Hmm. Now, if you consider this function fx, you see the integral of this function from this range minus infinity to mu, this much range, that would give us the area, this much area. So integral from minus infinity to mu fx dx, this integral, that should be actually, by definition, that should be is equal to value of the distribution function at the point mu. Okay, and our target is to define this quantity mu, this upper limit mu, in such a manner that this left hand side area should be is equal to half. Okay, therefore this capital F of mu, the distribution function, mind it, the distribution function capital F of mu, that should be is equal to half. That is the basic idea or a rough idea of defining the median, the middlemost value. Okay, and therefore we can say that the probability that minus infinity to mu, this probability should be is equal to half, and probability from mu to remaining plus infinity, that probability should also be is equal to half. Okay, but there is a problem regarding discrete distribution. There is no problem regarding continuous distribution. We can say that the median can be defined as f of mu is equal to half in this fashion. But for discrete distribution, we find certain problems. What are these problems? Let us try to discuss this kind of problem through two examples. Okay. You see, we know that for a discrete distribution, the distribution function f, the distribution function is actually a step function, this kind of function, monotone increasing or monotone non-decreasing step function. Okay, so if this is the we are considering this kind of step function over here, I am considering four different segments of this function capital F. So this is actually the distribution function of a certain discrete random variable. Mind it, the discrete random variable. In case of discrete random variable, the function f becomes a step function, and in case of continuous random variable, if this function capital F is a continuous function and its derivative would be piecewise continuous. We are discussing about the discrete distribution. Now, if you look at these figures, 0, 0.4, 0.8 and 1. We know that f of infinity is f of infinity is equal to 1. This is this is a property of the this distribution function. So it is clear that f of infinity is equal to 1. Again, f of minus infinity, that is equal to 0. So over here, f of minus infinity would be is equal to 0, that is obtained by this segment. And all these if you consider these values are increasing, 0, then 0.4, then 0.8. So these values are increasing. That means the function is a step function, and it is a monotone non-decreasing step function. Okay, and other properties are also satisfied by this kind of function capital F to be a distribution function. Now, what we need to do, what we need to have actually in case of median, f of mu should be is equal to half. Half means 0.5. Okay, half means 0.5. But look at this expression. You would not get any value of x for which f of mu would be is equal to 0.5. You would not get any value of mu such that f of mu is equal to 0.5. Got it? That is one problem. What happens over here? Actually, you can consider this kind of say this kind of coordinate axis, and then if we want to draw this figure of the function capital F, we will find that from minus infinity to 0, from the minus infinity to not 0, minus infinity to 1, in this first segment from minus infinity to 1. If you consider an open, this kind of open interval, minus infinity to 1, that would be the value of the function f(x) is equal to 0. And then from 1 to 3, it may be this kind of curve. Uh, this is closed. Then from 3 to 4, this may be this kind of curve. And from 4 to infinity, it is equal to 1, like this. Maybe from 4 to infinity, this is equal to 1 up to infinity. The problem is that over here, the quantity f of mu, if you consider f y is equal to f of x, if you consider y is equal to f of x, in that case you see for x is equal to mu, the value of y should be is equal to half. And the problem is that if you want to find out the equation of a straight line where this y becomes is equal to half, that the straight line would go through this kind of regions. That means in between two steps of the distribution function. This value half, this value, this is actually half, 0.5. 0.5. This is the value 0.5, and this 0.5 does not intersect any of these two branches, any of these two steps. Okay, so you see, we would not get any value of mu. So you see, we require some kind of modification of this definition. Hmm. We require some kind of modification of this definition of median. And what is the modification? So modification is proposed in this way, that suppose this is the, if it is the value of mu, hmm, then if you consider the left limit of mu, on the left limit there should be the probability mass should be less than is equal to half, and on the right limit it should be greater than is equal to half. Hmm. You see, if you consider this kind of limit, f of mu minus 0 is less than is equal to half, and f of mu plus 0 greater than is equal to half, then this kind of problems can be built. And as because the function f is a distribution function, so we know that a distribution function is always right continuous. Hmm. And therefore this right limit f of mu plus 0, that should be is equal to f of mu, and that's why this kind of modification, this kind of new relation, that is taken as the modified definition of the median. And this through this kind of definition, you see over here, if you consider this value, say mu x is equal to 3, if you make this target x is equal to 3, then f of 3 minus 0 would be is equal to 0.4. And f of 3, over here f of 3, the value of f of 3 is equal to 0.8, and that is greater than or is equal to half. Got it? So what we observe over here, we find that this mu is equal to 3 satisfies both of these two relations. So we can now take the median mu is equal to 3 for this kind of uh, given distribution function f. Got it? So this is one kind of modification that is required in order to deal this problem that arises over here. Hmm? So this is one kind of modification that is required for the definition of median. All right. And we get some other kind of problem as well. What is the problem? The problem is that sometimes what happens, sometimes this line for mu is equal to half or y is equal to half, this line sometimes coincides with this kind of step, coincide with one step. All right. And then what happens in such cases, any point throughout this step, any point is actually a candidate of being a median. Hmm. Any point in this step, if you look at this point, any point in this step over here, any point in this step would be a member, and that would be equally valid to be the median of the distribution. And in such cases, there is a confusion regarding the exact value of median. In fact, any value in this step can be taken as the median. So any value means the value should start from this zone up to this zone. Any value of x, any value of x would be a candidate of being a median. And in such cases, there should be two numbers. This is one number in this position, and this would be another number. Maybe this is our xk, x suffix k, and this value, suppose x suffix k plus 1, k plus 1, successive two values of the segment. And in such cases, consider we generally consider the middlemost value or the average value as the median. Okay, in such cases we generally consider the middlemost value. This corresponds to the point xk, and this segment corresponds to the value xk plus 1. So we generally consider half of xk plus xk plus 1, half of xk plus xk plus 1, all right, as the median of this distribution. Okay, that is the average value of xk and xk plus 1. So these two modifications are required. You see, for this kind of modification over here 0.5 is there, so in any value in between 3 and 4, any value in between 3 and 4 is a candidate of being a median. So what happens? We take the mean of these two values, the middlemost value in between 3 and 4, that is actually 3.5. Okay, this middlemost value is actually in that case taken, that is a convention. Mind it, this is a convention. Okay, the middlemost value is generally taken as the median. And so if we summarize the total discussion, you see the median can be defined into including all, incorporating all these modifications. The median mu either satisfies this property number 1 or this property number 2. In the property number 1, we have this kind of modification: f of mu minus 0 less than is equal to half, and f of mu greater than is equal to half. And in property number 2, if by chance this f of x is equal to half holds for all the points in between this segment xk and xk plus 1, in that case the middlemost point in between xk and xk plus 1, this middlemost point is taken as the median of the distribution. The next result that is required over here is that the first absolute moment about any point, about any arbitrary point, the first absolute moment about any arbitrary point is minimum when it is taken about median. What does it mean? It means the what is first absolute moment? The first absolute moment is defined as expectation of modulus, x minus a. Expectation of this kind of quantity, expectation of this kind of quantity, expectation of modulus x minus a, that is the first absolute moment. Absolute is used for modulus in order to denote this modulus. Absolute moment, the first absolute moment about this point a, about this point a, and the result says that this kind of first absolute moment would be minimum whenever this a becomes is equal to mu, the median. Got it? We had a similar result related to mean that says that expectation of x minus a whole square, expectation of x minus a whole square, this kind of expectation would be minimum whenever this a becomes is equal to the mean of the distribution. Second moment about about any point a is minimum whenever this moment is taken about mean of the distribution. So this result, what I am going to discuss over here, is a very similar kind of definition. It says that the in place of second moment, it says about the first absolute moment. Okay, so we are going to prove that the first absolute moment would be minimum whenever this a becomes is equal to mu, or in other words, whenever the first absolute moment is taken about this median. Okay, so let's prove this result. Over here, let's try to draw a line. Suppose the first absolute moment is taken about the point C. Over here I have considered this number C, the small c. All right, so suppose this is the position of small c. This is the position of small c, and two cases may arise. either c may be greater than mu or c may be less than mu. If by chance c becomes is equal to mu, then the result is obviously true. Hmm? So we are considering two different cases. One case is that c is greater than mu, another case is that c is less than mu. Hmm? So over here I have taken c is greater than mu. That means this should be the position of mu. Okay, c is greater than mu in this kind of situation. Now we are starting with this expectation of x minus c, expectation of modulus of x minus c, expectation of modulus of x minus c, and this expectation can be written in this way: integral from minus infinity to infinity modulus of x minus c fx dx. And in order to decompose this expression modulus of x minus c, in order to decompose this, we are taking the integral from minus infinity to c and then from c to infinity. These two kind of integral. In whenever in this integral minus infinity to c, you see x should be less than c and up greater than minus infinity. This is the range. Minus infinity to c, x is less than c. So when x is less than c, this modulus of x minus c can be written as c minus x. Okay, and in this second range over here, you see c should be less than x and that quantity should be less than infinity. So over here we observe that x is greater than c. X is greater than c, and whenever x is greater than c, in that case this modulus of x minus c can be written as simply x minus c. Okay, so these are the corresponding modification or the manipulation. Now now, what we are doing, this is actually our minus infinity, and this is our plus infinity. Okay. Now you see this expression, this integral from minus infinity to c, from this range. You see, this is the range, integral from minus infinity to c. This range can be decomposed into this kind of segment: minus infinity to mu and then mu to c. Okay, so that is the decomposition that I have used: minus infinity to mu and then from mu to c. All right, and afterwards this integral c to infinity, this integral c to infinity can be written as the integral from this extended range minus this extra range. This is the extra range. Actually, this is from c to infinity. This is the range under which we need to integrate. We are considering this much extra range for mu to c, and then we are deleting this much integral from mu to c. Okay, so in this way we are taking this integral, we are writing this second integral as first as an integral from mu to c, and then from as an integral from, and this is subtracted, this extra portion is subtracted from mu to c. So firstly the integral from mu to infinity, and then the excess integral, the excess range mu to c has been subtracted. Now you see over here it now becomes a bit complicated. How? At first we are dealing with this integral. Hmm? This integral c minus x, over here this integrand is c minus x. Okay, so this integrand c minus x is now decomposed in as mu minus x plus c minus mu. Okay, so this c minus x can be written as mu minus x plus c minus mu. Then this minus mu and then this plus mu will get cancelled, and ultimately we will have this c minus x. And as a result, this integral can also be decomposed into this integral where integrand is mu minus x into fx. This is the integrand, and the second integral would be c minus mu into fx. Okay, so in this way we are decomposing this first integral. Now we decompose this integral. X minus c is now decomposed as x minus mu minus of c minus mu. You see, with this minus sign and this minus sign, the sign of mu would be positive. So this positive mu has been adjusted with this negative mu. Okay, so this mu and mu are gets cancelled, and ultimately we will have this c minus x. And as a result, this integral from mu to infinity, that has been written as the difference of two integrals. The first integral is integral from mu to infinity x minus mu fx dx minus this integral mu to infinity c minus mu fx dx. Okay, and these two integrals, this integral and this integral, these are basically same type of integral. You see, over here the limits are mu to c, mu to c. Just the difference is that in place of c minus x, we have x minus c with this negative sign. So basically, with this negative sign, this integral and this integral, these two integrals, second and fourth integrals, are basically same type of integral, same integrals. So we combine these two integrals, this second integral and this fourth integral, and write them as 2 into c minus x fx dx. Okay. Now, uh, now over here. Over here you see, over here we are not we are what we are doing over here. You see, this first integral is written over here, this third integral is written over here, and this second and fourth integral, they together, from these two integrals we can take this c minus mu common. We can take this c minus mu common. All right, so we are taking this c minus mu common outside the integral sign, and then what we have, from minus infinity to mu fx dx, and this integral becomes from mu to infinity fx dx. And the remaining term, that is this term, it is not changed at all, it remains same. Okay, then what happens, you see, this integral, this much expression, that is written within this third bracket, within this box. What happens, you see over here, integral from mu to minus infinity to mu. This is the integral from minus infinity to mu, and this is the integral from mu to infinity. You see, if you look at this first line, if you look at this first line, this is this line. If you look at this first line over here, this was actually the decomposition. This was actually the decomposition of the integral modulus of x minus c fx dx. We had this type of expression, minus infinity to c, and then c to infinity. Over here we had c minus x and x minus c. And look at this expression. Look at these two expressions. Look at these two expressions, this integral and this integral. We have exactly similar integral. Just in place of c, in place of this c, we have mu over here. In place of this c, we have mu. What we have, integral from minus infinity to mu. Over here we had minus infinity to c, then mu minus x fx dx. We had c minus x fx dx, and in the second integral, in place of c to infinity, we have mu to infinity, and over here c, in place of c minus x minus c fx dx, in place of x minus c fx dx, we have x minus mu fx dx. So these two, this integral and this integral are exactly similar integral. Just in place of this number c, we have this number mu. Got it? And therefore we can say that this integral would be actually the same kind of integral like this. And that is actually modulus of x minus c. This was modulus of x minus c, and therefore we shall have over here modulus of x minus mu. Just in place of c we have mu. So this total expression within bracket would be represented as the integral from modulus of x minus mu fx dx. Okay, and you see this expression from mu to infinity. This expression can be written as the total integral from minus infinity to infinity, and then plus of minus mu to infinity. This is the integral mu to infinity. In fact, the integral from mu to infinity, mu to infinity, this integral should be represented in this way. You see, an integral from minus infinity to infinity minus the integral from minus infinity to mu. Okay, so we are operating this kind of we're just decomposing this integral over here as this integral and this integral. And what happens over here, what we observe is that this integral from minus infinity to mu and this integral from minus infinity to mu fx dx can be combined together. And what is this minus infinity to mu fx dx? That is actually our f of mu. So we know that mu is actually this f of mu. If this is a median, then f of mu should be is equal to half. And what about this integral minus infinity to infinity fx dx? This integral is actually is equal to 1. Okay, so the value of this expression is equal to half. The value of this expression is equal to half. So half plus half, that would be is equal to 1. And what is this? This value of this expression is equal to 1. So with this negative sign, the value of this second integral should be is equal to minus 1. This value, the value of this integral should be, this integral should be is equal to half, 1 by 2, and this value of this integral is also is equal to half. So actually half minus 1 plus half, so the value of this total expression within bracket, that value should be is equal to 0 basically. And therefore there would not be any contribution from this term at all. That contribution would be is equal to 0, and so effectively we will have only this term, the first term, and this last term. Got it? Effectively we will have this first term and last term. And what is this first term? This expectation, that would be an expectation of what? Expectation of x minus mu, its modulus. This expectation of this quantity will be the value of this integral, okay. So we can now write that what was left hand side. The left hand side, we started with this expectation modulus of x minus c. And this modulus of x minus c can now be written in this way. You see, this modulus of x minus c, this would be actually is equal to modulus of x minus mu. And what is this? This expression can be written in this fashion, and the contribution of this term, that would be is equal to 0. So this term would be actually is equal to 0. And therefore we will have only this first term, that is the first term, and this last term. So this is the last term. So this much is the final computational steps. This is the final step. And so over here we observe that you see over here the integral is from minus is from mu to infinity, mu to c, not infinity, mu to c, mu to c. Okay, so over here you see x lies in between mu and c. Therefore this c minus x, this is always a non-negative quantity, or greater than is equal to c. This c minus x will always be greater than is equal to 0 in this range. And therefore we can say that this integral is always greater than or is equal to 0, and the equality holds only when this upper limit and lower limit would be same. Mind it, the equality holds only when this upper limit and lower limit would be same. That means when c is equal to mu, and whenever we get this value, the equality, that means 0, whenever this value becomes is equal to 0, then only the value of this total right hand side becomes is equal, then only the value of this total right hand side becomes minimum. Okay, whenever c becomes is equal to mu, then only the value of this total right hand side expression becomes minimum. Otherwise, this is greater than x minus mu. This x minus mu is actually the minimum value that is achieved whenever this c becomes is equal to mu. Okay, whenever c becomes is equal to mu, then only we achieve this much minimum value. That's why the result says that first uh, absolute moment becomes minimum whenever c is equal to the median mu. Got it? Whenever c is equal to the median mu, then only the value of this first absolute moment becomes is equal to minimum, and this is the minimum value. The first term is the minimum value. So we prove this result for this case number 1. In this case, we have taken that c is greater than mu. Alright. And if c is less than mu, then by similar computation, we will get exactly same type of result. Modulus of x minus c is equal to modulus expectation of modulus of x minus mu. The first term, you see, the first term would be exactly same. Modulus of x minus c is equal to modulus of x minus mu. Over here as well, modulus of x minus c is equal to modulus of x minus mu plus 1 integral. And what kind of integral is this? Just to remember this integral, you see, a similar kind of expression would appear, either c minus x or x minus c. But over here, we need to remember that this expression, this integral would be a non-negative quantity, just similar to the previous case. This integral would ultimately be, by computation, this integral would ultimately be a non-negative quantity. And how to make this quantity a non-negative quantity? You see over here in the second case, c should be less than mu. So c is over here, and mu is greater than c. And so in between mu and c, we should have x. Got it? And therefore, in order to make this integral positive, you see over here we should have x minus c, not c minus x. Over here, x minus c, due to this kind of inequality, x minus c is greater than or is equal to 0. This is the technique by which we can remember this kind of integral. Integral from c to mu. Mind it, this is the integral from c to mu, because over here mu is greater than c. Mu is a larger number, c is a smaller number. In the first case, we had c as a larger number and mu as a smaller number. That's why we had the integral from mu to c. This was the lower limit, smaller number, and upper limit was the larger number. But over here, just opposite, this is c to mu. C is the lower limit, that is the smaller number, and mu is the upper limit, that is the larger number. So this much difference is there. So you need to remember all these small tidbits of this proof. Okay. And similarly, we can prove that if by chance mu becomes is equal to c, then only this value contribution from this term would become is equal to 0. And so we can say modulus of x minus c is greater than is equal to x minus mu. So in both of these two cases, this inequality holds, and the equality would appear, this equality over here, this equality would appear whenever this c becomes is equal to the median mu. All right. Now let's discuss about another measure of location, that is called mode. We have discussed about the mean and median. And now there is one more measure of location, that is called the mode. What is mode? In case of continuous distribution, okay, in case of continuous distribution of a random variable x, mode is the value of the variable x hmm, such that the density function fx has a local maximum at that point. Mode of a continuous random variable x is a point at which the density function fx has a local maximum value. Hmm. And in case of discrete distribution, the mode is a point xk. Xk is actually the value of the random variable x in the spectrum. Hmm. So, in case of discrete distribution, the mode is actually the particular value of the random variable x, or a point from that spectrum, such that the mass function at that point fk, value of the mass function at the point that is equal to fk, achieves the maximum related to the neighboring points. Okay, achieves the maximum related to the neighboring points. That means, suppose let us consider this kind of picture. Suppose this is the real line, and this is the value xk. This is the value xk. Okay, and this is xk minus 1. And this is our suppose xk plus 1, xk plus 1. Okay, and the value, this value at the point xk, this value would be maximum, or relative to its neighboring points. This value would be maximum relative to the neighboring points. This is the value of fk, that is the this quantity fk, and this fk would be greater than this value. At the point xk minus 1, the value would be is equal to fk minus 1, and at the point xk over here, this much, this value would be if k plus 1. Okay, so these two relations, that if k minus 1 less than if k and if k greater than if k plus 1, these two relations must be satisfied. And this kind of quantity is called mode of the distribution, or mode of the random variable. Generally this is denoted by capital M. Hmm. And sometimes we may have more than one mode of a distribution. And if it has two modes, then we call it bimodal distribution. If it has more than two modes, we call it multimodal distribution. If we have only one single mode of a distribution, then we call it unimodal distribution. Okay, and it can be proved that under certain conditions, if this the value of the median and mode, they are actually same in case of unimodal symmetric distribution. The value of mean, median, and mode, all of these become same in case of unimodal symmetric distribution. And if these are not if the distribution is not symmetric, then the value of median and value of mode would be different. And therefore this difference mu minus am, this is sometimes taken as a measure of skewness. This is sometimes taken as a measure of skewness. And if in certain distribution the mean exists, even then we can similarly define this difference. We can consider this difference m minus small m as another measure of skewness. All right. So we can define them in this way. And sometimes we require some unit free measure, and such unit free measure is defined as capital M minus small m minus capital M divided by sigma. That would be a unit free measure of skewness, where sigma is the standard deviation of the distribution. Therefore, in such distribution, the standard deviation must exist. Hmm. And the famous mathematician Carl Pearson found that whenever the skewness of the distribution is moderate, that means it is not very large and not it is very small. And in such cases, there is a statistical observation that by which he established a relation in between mean, median, and mode that is approximately followed in different distributions. What is this relation? The relation is that mean minus median, that is equal to 1/3 of mean minus mode. Mean minus median, that is equal to 1/3 of mean minus mode, provided the mean exists. Mean does not always exist. Therefore, if the mean exists and if the skewness is not very high or very small, it is not very much large positive number or very much small number. In that case, we get this kind of approximate relationship. So we need to keep in mind that this is an approximate relationship that is observed by Carl Pearson through their different statistical observations. Okay, so that's all for today. Thank you for being with me.